Hi, this is Seth, and in this video I'm going to show you how to conduct a t-test in R. I'll show you how to do a one-sample t-test, a paired samples t-test, and an independent samples t-test. Let's start with the one-sample t-test. Over on the left you can see I've already calculated the t-statistic using Excel. There's actually a faster way to calculate it, but I did it sort of piece by piece. This column contains our sample scores. We're comparing this sample mean, 55.5, to a hypothetical population mean of 50. Here we have the standard deviation of the sample size, the standard error of the mean, and the t-statistic. I also have the formula for a one-sample t-test right here. As with all t-tests, you take the difference between the means, which is the effect, and you divide it by the standard error, making it kind of a signal-to-noise ratio. How large is the effect compared to what would be expected due to pure noise, pure randomness? So if you subtract the hypothetical population mean of 50 from the sample mean of 55.5, then divide by the standard deviation over the square root of the sample size, you will get 4.09. Okay, so let's do that in R. I'm going to zoom in a little bit, maybe not that much. Okay, there are many ways to do this, but the fastest way is to start by creating a vector. Oh, and I should just let you know, I don't really code the right way or the way that I don't necessarily code the tidy way or the best practices way. I code in a way that works for me and gets the job done. So if it looks a little different than what you'll see elsewhere, that's why. Now, there are a variety of ways to run a t-test in R. I'll show you two ways. The first thing we might want to do, though, is create a vector, which is like a column or a row of data, kind of like we have this column of data right here. These are our sample scores. This code creates a vector of data, and I'm calling it X. I'm doing this using the C function. That means combine, or some people will say concatenate. It just takes whatever goes inside the parentheses and turns it into a kind of list that's called a vector. This part at the end just says, after you run the code, go ahead and show me what the result is. So when I run that, it assigns that vector of values to X, and here you can see it shows us what they are. That's our column or row of data. Now, the fastest way to do a t-test is to use the t-test function like this, t.test, open parentheses. You can say X, which is the vector of scores that you're running the t-test for, comma. If it's a two-tailed test, you can say alternative equals two-sided, comma. Then enter whatever, well, we should say mu equals, and then you enter whatever value, whatever hypothetical population mean you're comparing your sample mean to. And in this example, you can see I'm comparing it to 50. So I'll just say 50. Then just run that line of code. All right, let's see our results. Yep, looks like R gets the exact same answer that we found in Excel. The t-statistics is equal to 4.09. You can also see it calculates a p-value. This is the probability that we would see an effect at least this large, just due to chance. In other words, if the null hypothesis is true. It also gives you the 95% confidence interval, and you could change that. You could add another argument to your t-test function to specify if you wanted a 90% or a 99% confidence interval. It can do that easily. By the way, if you want to see more about this function, you can use help, open parentheses, t-test, and pull up the documentation. And there you can see all the different ways that you could specify this. I only used some of these arguments. You don't have to use them all. Now, I don't know if anyone but me would ever care to do this, but we could also calculate the t-statistic in a much more piecemeal fashion, just like we did in Excel on the left. So let's do it that way. We can say M for the mean is equal to, you can use the function mean of x. Okay? And that's 55.5, same answer that we got when we calculated with Excel. Okay, we could say mu is equal to 50, and we just know that because that's what we chose for it to be hypothetically in this example. So that's 50. To get the standard deviation of a sample, you can use SD, open parentheses, x. All right, that will, let's go ahead and assign that. Let's call that S. So S is equal to the standard deviation of X. So let's run that code and then make it show us what we get. It is 4.25. Same answer we got over here, 4.249. We could calculate the sample size. Let's call that N equals, you can use the function length. This finds the number of elements in an object. So the length of X is the number of scores in X. Whoops. Okay. Run that, and it is 10. The degrees of freedom are equal to n minus 1 in this scenario. If we run that, we would find degrees of freedom are 9. The standard error is equal to the standard deviation divided by the square root of the sample size. You can use this function sqrt to calculate a square root. Okay, so we're going to assign the standard error to whatever that is, and then make it show us what the answer is. It's 1.34371, exactly what we found in Excel. Okay, and so now we have all of the parts that we need to calculate the t-statistic. I think t is already an object, so I'm going to say t-stat is equal to, and we can just use the formula. It's the sample mean minus the hypothetical population mean divided by the standard error. All right, so let's see what we get. 4.093, same answer that we got in Excel, and whenever we use this much faster version. Oh, if you want to know the p-value, you can use this code, pt. So that's the p-value for a t-distribution, for a t-statistic. And we're interested in our t-stat, comma, and then the degrees of freedom, which are 9. So what this is going to do is it's going to find the proportion of the distribution for, the t distribution for 9 degrees of freedom. It's going to find the proportion that lies to the left of our t statistic. Now, this isn't going to give you the p-value that you're used to seeing. Let's see what this does. It gives us 0.99, but we don't want the proportion to the left of the t-statistic. We want the proportion that's more extreme than the absolute value of our t-statistic. If it were a one-tailed test, you could use 1 minus that amount. That's not the only way to do it, but it's a fast way. That gives us the proportion of the distribution that's more extreme. But since I think we said above, we treated it as a two-tailed test above. If you want to do that here, we could say 2 times and then put all of that in parentheses. So 2 times that amount. That's our p-value, 0.0027. And let's just double check. Is that what we got before? Yes, that's what we got whenever we just used the t.test function. Okay, there you go. One sample t-test. Next, let's look at a paired samples t-test. I don't know, probably also called a dependent samples t-test, maybe, or a t-test for related samples. Here's the scenario on the left. We have 2 distributions, 2 samples of scores, and they're connected in some way. Maybe it's the same person at 2 different points in time. Well, the way this sort of t-test works is we have 2 columns. We have a t-test formula that works for a single column. So basically what we do is we turn the 2 columns into one column by subtracting one from the other, and then we just do a t-test like normal. So here you can see I created a difference column. I just subtracted one from the other. Which one you subtract from which will matter if they're at different points in time, but doesn't really matter in this situation. Here we have the mean of the difference scores. That's what the M subscript D means. It's the mean of the difference scores. Here's the standard deviation of those difference scores. The number of scores, well, the number of difference scores, there are 9 of them here. This is the standard error of the mean for these difference scores. In this case, the hypothetical population mean that we're comparing to is 0, because if the null hypothesis is true, then the average difference score will be 0, because the prototypical null hypothesis says there's really no difference between the two sets of scores on average. Okay, and then the t statistic is actually just like normal. It's the mean of the sample minus the hypothetical population mean. Well, anything minus 0 is itself, so you could just think of it as the mean divided by the standard error of the mean for the different scores. So it's -3 divided by 0.5, which is -6. A nice round number that makes you know you're looking at made-up data. Okay, let's do it in R. Okay, let's say x1 is equal to, and I'm just going to list all these, 4, 6, 5, 5, 6, 4, 3, 8, 6. Okay. And then x2 is equal to 7, 7, 8, 9, 9, 7, 9, 9, 9. Okie dokie. Okay, we could now run the t-test with a single line of code. So actually, yeah, let's just do that. We can use t-test, except now we're going to enter some different specifications from before. First, enter your first sample of data, that first vector we created, x1, comma. Then your second vector, which we named x2, comma. You could, the way this works, you could just say two-sided right here. That would be a positional argument. If you want, you can spell out the details. You can say alternative equals two-sided. That's fine. But because it's expecting this in the third position, you could just do this briefer code where you just say two-sided, comma, and then we'll say paired equals true. So it's a t-test, but now there are two samples that we're looking at, and we're saying, by the way, they are paired, and it's a two-tailed test. Okay, let's see if it works. The mean difference is -3. That is the same thing we found up here. And our t-statistic is -6, same as we found before. Also, we have a p-value, 0.0003. So not particularly likely if the null hypothesis is true. Once again, I'm going to show you how to do it piece by piece in case you like to see how all the parts fit together. We could say, well, let's create a vector called diff. All right, this is going to be x1 minus x2. All right, I'm going to say semicolon diff to make it show us the result after it does it. There you go. These are the values, -3, -1, -3, -4, same as before. We can find the mean of the difference, or I guess I can assign it, we'll say mean of the difference, MD. That's the mean of that difference vector that we just created. All right. What is that? It's -3. We knew it would be. We can find the standard deviation of that. Maybe I'll call it s dot d, because sd is the name of a function. Okay, like before, we can say, give us the standard deviation of the difference scores, and it's 1.5, same as we got before. The sample size is the number of difference scores. So I'll say nd is the length of diff. It is 9. Same as we got before. Then I'll say standard error of the difference scores. Well, it's the standard error of the mean of the difference scores. Sorry, I know that's a lot. That's going to be equal to the standard deviation divided by the square root of the sample size. Let's see what we get. SED 0.5, same as we found in Excel. I guess we could say mu is equal to 0 if you want, just for fun. You could do that or you could just leave it out of the calculation entirely. Okay, and let's calculate our t-statistic. It's going to be equal to the mean of the different scores minus, well, 0, or I guess you could say mu, or you could just leave it out. Let's just leave it out because the mean minus 0 is the mean. So we have the mean of the different scores divided by the standard error of the mean for the different scores. And I'll do a little semicolon so we can also see the result after we run it. -6, that's our t-statistic. Same as we found in Excel, same as we found using the faster R code. Let's go ahead and calculate the p-value in this piecemeal way as well. Okay, so this time we have a negative t-statistic, which means if we just go straight to pt, so the probability or the proportion of scores to the left of a t-statistic, our t-statistic has creatively been named t-stat, and we have 8 degrees of freedom. I guess I didn't calculate that here, but in this scenario, the degrees of freedom are n-1. We have 9 different scores, so it's 8. Now, if we were doing a one-tailed test, this would just immediately give us the answer, 0.00016. But this is a two-tailed test, so we're going to say 2 times that, which is 0.000323. Yeah, same thing that we got before. Now notice, because this is a negative t-statistic, it's -6. That's why I don't need to use 1 minus like I did for a positive t-statistic, because we really do just want the proportion to the left of our t-statistic. That's more extreme than -6. But we also want to know what's more extreme than +6, so we just double it. Okay, cool. Paired samples t-test in R complete. Okay, let's lastly do an independent samples t-test. Now this one is a bit uglier. I switched to calculating these various statistics for the 2 samples in this vertical fashion because it's just easier for me to grasp that this is the mean of each one, the sample size of each one. Now, if we assume that the variances of the 2 samples are equal, which I apologize, I'm not going to go into explaining how t-tests work in great depth in this video. This is really about how to do the calculations in R, but it's a bit uglier. If we assume the variances are equal, then we might pool them first. We would pool the variances to get a pooled variance right here, and then that's actually what we use to calculate our standard error. But although it's considerably uglier than the others, it's really just the same formula. It's the mean difference. It's the effect divided by the standard error. It's just an ugly standard error. It's an ugly path to get there. But regardless, here you go. I've calculated the mean of each sample. These are 2 independent samples, so they're not connected to each other. There should be no relationship between this person's 9 and this person's 3. It's not like the same person at 2 points in time. They're not spouses. So we have the mean for 1, the mean for 2, standard deviation for each of them. I also calculated the variance for each of them. You can get that just by squaring the standard deviation. The sample size for each is 8, which means the degrees of freedom for each is 7, and the overall degrees of freedom is then 14. I pooled the variances right here. I'm just doing what this formula says. You multiply each variance times its degrees of freedom, add them together, then divide by the overall degrees of freedom. You're just sample weighting the variances. If you understood the concept of sample weighting the mean that's talked about in other videos, it's the same concept. We're just doing it for the variance. And then the standard error, I just used this exact same formula right here. Pooled variance divided by the first sample size plus pooled variance divided by the second sample size. Take the square root of whatever you get, and it turns out to be 1.34 in this case. Then just divide the mean difference by that, and you get your t-statistic. So we should be coming to 2.245. Let's see what happens. Okay, first of all, we're going to say, let's create a vector that has these values. Okie dokie. I'll go ahead and run it. Let's do that also for the second sample. Okay. If you want to run it with a single line of code now, as before, you can just say t-test, open parentheses, x1, x2. This is a two-sided t-test, a two-tailed test. And then let's say the variances are equal. So let's say we are assuming that the variances are equal. So we're going through this procedure using this formula. Not necessarily the assumption you want to actually make, but just showing you how to do it. You can say var.equal equals true. So that just means it's going to assume the variances are equal, and it's going to pool them. Okay, I think that's all we need. So let's see what we get. Okay, the mean of x is 9, mean of y is 6, like we expected. Okay, 2.245 is our t-statistic, same as we got right here, except r is rounding for us. Overall degrees of freedom are 14, p-value is 0.041. That looks right. Okay, now, probably most people have already closed the video. Probably most people only watched the part where I showed them how to do it with a single line of code. But if you're still here, you want to see how to do it in a piecemeal fashion, let's jump in. Okay, let's calculate our two means. So the mean 1 is the mean of x1. Let's see what that is. It is 9. That's a good sign. That's what we got before. Let's do that for the second mean. Whoops. It is case sensitive, so make sure not to mess that up. The mean of that sample is 6. Let's find the standard deviation for the first. It's 2.507. Yep, that's what we got before. And for the second, 2.83, same as we got before. Oh, I guess I didn't really need to calculate the standard deviation, did I? Oh, well. If we want the variance, we could say VAR of x1, and that gives us 6.285. That's what we got before. Or you could say the variance of 1 is equal to the standard deviation of 1 squared, because that's what the variance is. It's the standard deviation squared. Whoops. Same answer. But I'll just keep it like this. Variance, the second variance, VAR, open parentheses, x2. Okay, then we say do it and then tell us what it is. It's 8, same as we got in Excel. Our first sample size is, we could say the length of x1. All right, so that's 8. Second sample size is the length of x2, which is also 8. Let's go ahead and calculate degrees of freedom. That's for the first one, it's n minus 1. That should be 7. It is. df2, our second degrees of freedom, well, that's the second sample size minus 1. We get 7. To pool the variance, let's see, I'll call it var.p for pooled. Let's see, so we're really just sample weighting the variance. So we'll say degrees of freedom 1 times the first variance plus the df2 times the second variance. So we're multiplying each variance times its degrees of freedom and dividing by df1 plus df2. It's a little silly to pool the variances in this situation because the sample sizes are the same. And when the sample sizes are the same, you can just directly average them. So to sample weight something when the sample sizes are the same does nothing. But I'm just going to walk you through it because if the sample sizes were different, you would definitely want to use this formula. Okay, so let's hope that this gives us 7.14. It does. Okay, then let's find our standard error. That is equal to, check right over here, it's going to be the square root of the pooled variance divided by N1 plus the pooled variance divided by N2. All right, let's see what happens. Do we get 1.336? We do. Okay, then the t statistic is just, well, t stat is mean 1 minus mean 2 divided by the standard error, and that is equal to 2.24499, same as we got over here. Okay, that's a positive value. To find the p-value, we could say 2 times, open parentheses, 1 minus pt, open parentheses, t-stat, comma, degrees of freedom. Now, in this case, we have 14 degrees of freedom because the sample size is 16. It's like you're using that n-1 formula for each sample. So n-1 plus n-1, 7 plus 7 is 14. Let's see if it works. 0.04144, is that what we got before? Yep. Boom. Perfect. Okay, there you go. Let's do one last thing. Let's say we were not assuming equal variances, which actually is probably safer. We could just say, do a t-test for x1 and x2. It's still two-sided, but we don't have to do anything else. By default, var equal is false. Okay, so I'm just going to leave it out, and it will default. When we do this, everything's the same. It's calculating the same t statistic, etc., but we use different degrees of freedom, and so the p-value comes out a little bit different, or maybe a lot of it different. But in this case, pretty close. This is called a Welch t-test, when you don't assume the variances are equal. The calculation's actually a lot easier too. You don't have to pool the variances. Okay, cool. More than you wanted to know about calculating t-tests in R. There you go. Have fun.